Hi, I'm Forrest Groos Rosenfeld. So my poster is talking about the ssVEP, the steady state visual evoked potential, and what I was looking in with this project with two pilot studies is are there interactions between transient ERP components and the steady state visual evoked potential? And in this case, this is during a visual search paradigm. So there's a classical theory of superposition. The ssVEP is generated by linearly superimposed transient ERPs, and that's what's producing the steady state or any other linear mechanism. So in the literature, it's a bit debated, and it's really difficult to actually show empirically what is actually driving the steady state. Is it linear superposition, or is it a nonlinear generator of some kind? So what I did with this study was assume that the steady state is an oscillatory generator, and working from that, if it is an oscillatory generator and this generator is interacting with other networks, so in this case an N2PC generator, whether it be the N2PC generator is probably not an oscillatory generator, but it could be an excitable network because the task is to search for a target. Can the oscillatory ssVEP generator, will it couple in any way with this excitable network that is doing visual search that leads us to the N2PC? So these were two pilot studies, and the first pilot study was meant to look at spatial interactions. So the N2PC is a lateralized potential that is enhanced for target only if it's on the left or the right hemifield. So can we anticipate the steady state enhancing for lateral positions only versus medial ones, so top-bottom? And the second hypothesis was if it's not spatial, perhaps it's temporal, the interaction. So there's been a lot of research that tries to look at temporal, like timing effects of the steady state, such as the duty cycle that influences the output. What I was doing here was looking at the cycle of how long it takes for an N2PC to develop, which is 200 to 300 milliseconds, and if we time the steady state to match the N2PC window, would we see effects here? So that if it matches, that perhaps a coupling mechanism is happening and we find enhancement when the steady state frequency matches the N2PC window. So what we ended up so I guess I should explain the paradigm. This was a visual search paradigm where we had 4 positions, so top, bottom, left, and right. In each position, there are checkerboards that are flickering, so it's a pattern reversal steady state. So black and white checkerboards are exchanging. This drives the steady state at 3 different frequencies. So there was a target frequency, a tagged distractor frequency, and then another frequency for the other 2 distractors that I wasn't specifically investigating. So I just tagged one of the distractors to compare it against the target. The target is going to be an embedded capital letter T among the checkerboard, and the distractor letters are L embedded in the checkerboard. The frequencies are counterbalanced for both experiments. The frequencies are counterbalanced. The position is randomized, and the orientation of the T and L is randomized. So the task of the participant is these checkerboards are flickering for 1.5 seconds, at which time the target and the 3 distractors become embedded into the ongoing flickering, and they have to determine if the target, first they have to find the target without moving their eyes, is the target upright or sideways, so vertical or horizontal. That's the same task for both experiments. Experiment 2 was just slightly longer, and I made it slightly more difficult for them to find the target. But really the only thing that was changed was, well, I'll get to the second experiment in a second. So experiment 1, what we ended up finding was, in fact, the amplitude of the steady state enhanced only for lateral positions. Top and bottom, once the target came on the screen, and that period, that epoch that we analyzed of the target coming on the screen, only to the lateral targets did the steady state enhance, not for top bottom. The phase, which is also very interesting, the phase did not change. And this was something not published that I found frequently with the steady state, is when there is a disruption. The phase goes on unperturbed. It's the amplitude that takes a hit. Nevertheless, what we found here was that the amplitude enhanced for lateral positions. So that was interesting. Okay, this looks like there might be an interaction with N2PC. In what way? I wasn't sure, but the big downside is that there was a confound. I made a coding error, and my orientations of the T and the L's were not randomized as I thought it would, as I thought it was. So it wasn't until my very last participant, these are 25 people that are averaged together for this first experiment, the very last person told me, when it's on the right, it's always upright. When it's on the bottom, it's always sideways. When it's on the left, it's always upside down. And when it's on the top, it's on its side. So that was disheartening because that is a huge confound. The fact that in the lateral positions, the target is always vertical, which could lead to facilitated processing for the target. So that was a confound. So as far as the conclusions for my experiment 1 pilot study, honestly, I just need to do more experiments because I'm not sure if we can really say that this enhancement to lateral targets has anything to do with the actual N2PC effect. Now, experiment 2 was more exciting. So with this, I designed it so that there were still 3 frequencies. So there was a target frequency, a tagged distractor frequency, and then the other 2 stimuli were at the other frequency. Now, either the target frequency hit the N2PC window, like what I said. So that means the cycle, the length of the steady state cycle matches what it would take for an N2PC to develop, so 200 to 300 milliseconds, or it missed that window. And in the poster, you can see I have a table that breaks down what that range would be. So the hit zone or the hit frequency was selected to hit that 200 to 300 millisecond, as well as controlling for harmonics, so the second harmonic, as well as intermodulation frequencies. So this took a while to actually figure out 2 frequencies that when they interacted didn't produce something that fell in the hit zone or the hit frequency. So, and that was counterbalanced within person. So they would have trials in which the target would be in the hit zone. They'd have trials in which the target fell outside of the hit zone. So what I ended up finding here was really interesting, is there was enhancement for both frequencies for the target, but it was more so when it fell in the hit zone. And more than that, as far as a replication study from experiment 1, the bottom target also enhanced. So it wasn't the case that it was just the lateral positions. The bottom, especially the bottom, actually was much stronger. Now this was, as far as why the bottom target location was so much stronger, was again another experimental confound. So in the experiment room, I couldn't manage to get eye level to be at the center of the screen. Their eye level, just because of how much you could raise the chair, their eye level was actually more fixated on the bottom location, the bottom target. They could still perform correctly and they could still see everything, but as far as visual input, most of it was coming from the bottom target. And I think there's also some research showing that the bottom of a stimulus it has greater facilitation, and you actually see that in the steady state. Regardless, experiment 2 ended up not finding that lateralized effect, that it didn't matter where the target was. It became enhanced once the target came on, steady state amplitude became enhanced. So this goes also with the steady state research, that we find that space doesn't matter where it is in location. You'll find if it's something important to pay attention to, the steady state will become enhanced. But what was interesting is that when the steady state frequency cycle fell into the N2PC cycle, it ended up enhancing more than just outside of the range. So the frequencies we're talking about, I should probably say, because it's hard to do knowing who's looking at what point at the poster, but the hit zone, the hit frequency was 8.57 hertz. So not barely on the alpha edge, because I also wanted to stay away from any alpha effects. And the miss zone was 5 hertz, so I think it was 5.7 hertz. So also what was a little encouraging with these results potentially being a true frequency thing, is that normally we would find for lower frequencies greater amplitude. And what we ended up seeing is that for the 8 hertz, the amplitude was actually much greater than the 5 hertz, and that's why I showed the frequency spectrum. So we don't have that 1 over f function. We find true greater enhancement to the 8.5 hertz in the hit zone. So as far as implications go, so these are really two pilot studies. A lot went wrong with these two studies, like I mentioned. The second experiment was only 15 people. This work was done at Vanderbilt, and I was running up until the very last day of my postdoc at Vanderbilt before I moved back to Florida. So I only could get 15 people for this pilot study. So there's still a lot of work to do, not just quantity-wise, running more people, running more experiments, but adjusting the parameters, making sure that my claims actually have anything valid to them. So my implications, what I want to leave with this is I think we need to move beyond the linear superposition theory. It's not enough to explain a lot of the stuff that we see with not just steady state, but how the brain works in general. I believe there's some type of coupling mechanism that's going on as far as how. There's a lot of work still to figure out what that is, but these are definitely interesting results that, of course, most ssVEP researchers know it matters what frequency you're in, and it matters how your frequencies are possibly interacting and where they are in space. So these are all things we need to seriously consider before we jump to any conclusion of attention is doing this, saliency is doing this, when it could be a physical thing as far as like the physical properties of the EEG. So I think that was over 2 to 3 minutes, but I hope you enjoyed listening, and I hope you enjoy the poster, and you can find my email address at the bottom if you want to ask me more questions. All right, thank you for listening.